This is question 4 from the 2005 MMPC round 2. In this question, the solution guide was fairly brief, so let me go over this question in a little bit more detail. So we're given a function, some rational function, and this is called f1, and then like f2, f3, f4, and so on will be defined by composing this function with itself n times, right? F of n plus 1 of x is f of fn of x. Okay, so it's written exactly like this on the question. It can be shown that f of 35 equals f of 5. I guess that means that you're allowed to use this fact without confirming that it's true. So the actual question is a two-parter. First one, find g, so that f of g of x equals g of f of x equals x. In other words, this means we're looking for the inverse function. And the second part is to calculate f sub 28. All right, so let's do this one first, the inverse function. There's at least two good ways to find the inverse function. One way that you're probably familiar with is write down y equals f of x and then switch the x and y and solve for y. So I can write, using a better marker, I can write x equals 2y minus 1 over y plus 1, and I can solve for y. And that'll be my g of x. I'm sure you guys can all do that, so let's just review a graph of rational functions and try to find a different way to find this solution. So this is a rational function. It's a transformation of 1 over x, essentially. It's got a vertical asymptote at -1, and it's got a horizontal asymptote at y equals 2. And it's slightly less than 2 when x is a large number. So I guess I could also say it's got an x-intercept at 1/2. I want to get that down. So the shape of this function looks like this. And if I just think about a reflection of this function across the line y equals x, I can see that the inverse ought to be another transformation of 1 over x, right? So f inverse of x should be some function where, because 2 is not in the range of f, 2 should not be in the domain of f inverse. So I should have an x minus 2 down below. -1 is not in the domain here, so that should not be in the range of the inverse. So I'm going to want my horizontal asymptote of this function to be at -1. Now, the only thing I need to know to settle this down is what should be my x inverse, what should be my y-intercept of the inverse function. So right here, the y-intercept is -1. So the x-intercept of the inverse should be -1. So if I just think about doing a reflection, this ought to be my answer. And it's up to you. Is it easier to think about this graphically, or is it easier to go through the algebra? You can probably do either one in a fairly reasonable amount of time. Okay, but either way that you get this function, how can we use that to help us in part B, or do we even have to? Well, the thing we have to realize is that f35 of x equals f5 of x. The way this function gets built up is it's kind of additive like this, right? I'm taking f of f of f of f of f 35 times here. Well, okay, so I'm taking f composed with itself 30 times of the first 5, right? But if this is true, this means that f30 is just the identity function. But again, another way we can write f30 is f of f28. So in order to isolate f28, I need to get rid of two of these f's. So f28 of x equals g of x. So I could just calculate that composition of functions kind of directly, negative, and then for x I plug in the whole function again, right? Negative x plus 1 over x minus 2 plus 1 divided by negative x plus 1 over x minus 2. And I should probably simplify that, but in the interest of time, I'll leave it here. It's a correct answer. You might lose a point for not simplifying it, but we'll come back to that later. What I want to talk about right now is there's a little bit of hidden math behind this question. One reason I like MMPC is not just answering the questions themselves, but thinking about where they came from. So the math behind this question is that there's a strong relationship between the matrix of matrix arithmetic, or the inverse of a matrix, and rational functions. Okay, so think about just any 2x2 matrix. Now you might have only ever used these matrices to solve a system of equations, solve a linear system, and that gives you a really limited idea of what matrix is really useful for. If you learned how to do that, you might have also learned how to do some matrix multiplication or other kinds of operations with matrix, and you kind of learned that, but I don't know if you saw any applications. So here's one. If we relate the rational function where a, b, c, and d coefficients, those can just go into a matrix, right? We can do this for two different functions, or possibly, like, this could be the same function twice, right? So how does this work? Well, if you're going to compose f of g of x, okay, I can just write it out like I did over there. And if we simplify this, multiply top and bottom of the fraction by jx plus k, and simplify, then we get another function of the same form, rational function. So we get a coefficient times x plus a constant divided by a coefficient times x plus a constant. Where do these confusing looking constants come from? Well, they're the exact same thing that you get if you multiplied the matrix F with the matrix G. Okay, so one thing you can see is that if G is the inverse matrix, so if F times G is 1, 0, 0, 1, then this function is x plus 0 over 1, or just x. So the inverse matrix will help you find the inverse function. And even if they're not an inverse, the two matrix, matrix multiplication will help you to calculate the inverse function. And I mean, you're doing the same math either way, but it's nice to see that these matrices, which might not have been developed for this type of function, they can still be used. And it's also easier to keep track of all your coefficients when you get rid of the fraction bars and you get rid of the x's, and you avoid having these kind of compound fractions. So, matrix is a good computational tool, and it also shows some ways that math can be connected that you might not have thought of before.